This is about what can be known no matter how the universe works, and what you can do with that knowledge because of how the universe works. Peace.
Attempt to make sense of quantum theory is that, roughly speaking, the innovation is going to come in how we think about causation, how we think about inference, right? So those are going to be two really important elements that we need to unscramble. Like what's about reality and what's about our knowledge of reality. So I want to know what's about causation, what's about inference. And so roughly speaking, for me, there's going to be quantum notions of causation and inference, and they are going to be innovations relative to the classical notions of causation and inference, much like, if you think about the notions of space and time, relativistic notions of space and time are innovations on the pre-relativistic notions. So they're still recognizably about space and time, but there's certain aspects of the conventional notions that we have to give up. And so it's similar here, that there's certain aspects of the notions of causation and inference that we're going to have to give up when we go to quantum theory.
This is the first two papers beyond the Analavos of the Great Hypersigil. And with these two papers, we really establish it is what it is.
New proof reveals fundamental limits of scientific knowledge. A new proof by SFI. Professor David Wolpert sends a humbling message to would-be superintelligences. You can't know everything all the time. The proof starts by mathematically formalizing the way an inference device, say a scientist armed with a supercomputer, fabulous experimental equipment, etc., can have knowledge about the state of the universe around them. Whether that scientist's knowledge is acquired by observing their universe, controlling it, predicting what will happen next, or inferring what happened in the past. There's a mathematical structure that restricts that knowledge. The key is that the inference device, their knowledge, and the physical variable that they may know something about are all subsystems of the same universe. That coupling restricts what the device can know. In particular, Wolpert proves that there's always something that the inference device cannot predict, and something that they cannot remember, and something that they cannot observe. In some ways, this formalism can be viewed as many different extensions of Donald McKay's statement that a prediction concerning the narrator's future cannot account for the effect of the narrator's learning that prediction. Wolpert explains, perhaps the simplest extension is that when we formalize inference devices mathematically, we notice that the same impossibility results that hold for predictions of the future McKay's concern also hold for memories of the past. Time is an arbitrary variable. It plays no role in terms of differing states of the universe. Not everyone can be right. What happens if we don't require that an inference device know everything about their universe, but only that it knows the most that could be known? Wolpert's mathematical framework shows that no two inference devices who both have free will appropriately defined and have maximal knowledge about the universe can coexist in that universe. There may or not be one such super-inference device in some given universe, but no more than one. Wolpert jokingly refers to this result as the monotheism theorem, since while it does not forbid there being a deity in our universe, it forbids there being more than one. As an example, suppose that Bob and Alice are both scientists with unlimited computational abilities. Moreover, suppose that they both have free will, in that the question Bob asks himself does not restrict the possible questions Alice could ask herself, and vice versa. This turns out to be crucial. Then it is impossible for Bob to predict or retrodict what Alice thinks at another time, if Alice is also asked to predict what Bob is not thinking at that time. Wolpert compares this proposition to the Cretan liar's paradox, in which Epimenides of Knossos, a Cretan, famously stated all Cretans are liars. The unlike Epimenides statement, though, which exposes the problem of systems that have the capability of self-reference. Wolpert's reasoning also applies to inference devices without that capability. In addition, in Wolpert's formalism, the same scientists, considered at two different moments in time, is two different inference devices. So while it could be that's an inference device is a super inference device at one moment, they could not be so more than once. Again, tongue-in-cheek, he refers to this as the deism theorem, since it allows there to be a deity that knows the most that could be known at the beginning of the universe, but forbids there ever being so knowledgeable again, because it does not rely on specific theories of physical reality, like quantum mechanics or relativity. The new proof that presents a broad set of limits for exploring the nature of scientific knowledge. None of these results, limiting knowledge acquired by prediction, relies on there being chaotic processes in the universe. It doesn't matter what the laws of physics are, or if Alice is more computationally powerful than a Turing machine, says Wolpert. All of this is independent of that, and it's much broader ranging. This research is progressing in many different directions, ranging from epistemic logic to a theory of Turing machines. In particular, Wolpert and his colleagues are creating a more nuanced, probabilistic framework that will allow them to explore not only the limits of absolutely correct knowledge, but also what happens when the inference devices are not required to know with 100% accuracy. What if Epimetheus had said, the probability that a cretin is a liar is greater than X%, moving from impossibility to probability could tell us whether knowing one thing with greater certainty inherently limits the ability to know another thing. According to Wolpert, we are getting some very intriguing results.
And some of those results apply to our physical world and what it's really capable of.
Quantum physics problem proved unsolvable. Gödel and Turing enter quantum physics. A mathematical problem underlying fundamental questions in particle and quantum physics is provably unsolvable. According to scientists at UCL, Universidad Complutense and de Madrid, ICMAT, and Technical University of Munich, it is the first major problem in physics for which such a fundamental limitation could be proven. The findings are important because they show that even a perfect and complete description of the microscopic properties of a material is not enough to predict its macroscopic behavior. A small spectral gap, the energy needed to transfer an electron from a low-energy state to an excited state, is the central property of semiconductors. In a similar way, the spectral gap plays an important role for many other materials. When this energy becomes very small, i.e. the spectral gap closes, it becomes possible for the material to transition to a completely different state. An example of this is when a material becomes superconducting. Mathematically extrapolating from a microscopic description of a material to the bulk solid is considered one of the key tools in the search for materials exhibiting superconductivity at ambient temperatures or other desirable properties. A study published today in Nature, however, shows crucial limits to this approach. Using sophisticated mathematics, the authors proved that, even with a complete microscopic description of a quantum material, determining whether it has a spectral gap is, in fact, an undecidable question. Alan Turing is famous for his role in cracking the Enigma code, said co-author Dr. Toby Cubitt from UCL Computer Science. But amongst mathematicians and computer scientists, he's even more famous for proving that certain mathematical questions are undecidable. They are neither true nor false, but are beyond the reach of mathematics. What we've shown is that the spectral gap is one of these undecidable problems. This means a general method to determine whether matter, described by quantum mechanics, has a spectral gap or not, cannot exist, which limits the extent to which we can predict the behavior of quantum materials, and potentially even fundamental particle physics. $1 million to win. The most famous problem concerning spectral gaps is whether the theory governing the fundamental particles of matter itself. The standard model of particle physics has a spectral gap. The Young-Mills mass gap conjecture, particle physics experiments such as CERN, and numerical calculations on supercomputers suggest that there is a spectral gap. Although there is a $1 million prize at stake from the Clay Mathematics Institute for whoever can, no one has yet succeeded in proving this. Mathematically, from the equations of the standard model, Dr. Cubitt added, it's possible for particular cases of a problem to be solvable, even when the general problem is undecidable. So someone may yet win the coveted $1 million prize. But our results do raise the prospect that some of these big open problems in theoretical physics could be provably unsolvable. We knew about the possibility of problems that are undecidable in principle since the works of Turing and Gödel in the 1930s, added co-author Professor Michael Wolff from Technical University of Munich. So far, however, this only concerned the very abstract corners of theoretical computer science and mathematical logic. No one had seriously contemplated this as a possibility, right in the heart of theoretical physics before. But our results change this picture from a more philosophical perspective. They also challenge the reductionist's point of view, as the insurmountable difficulty lies precisely in the derivation of macroscopic properties from a microscopic description. Not all bad news, co-author Professor David Perez Garcia from Universidad Complutense de Madrid and ICM Mat said, "It's not all bad news, no. The reason this problem is impossible to solve in general is because models at this level exhibit extremely bizarre behavior that essentially defeats any attempt to analyze them. But this bizarre behavior also predicts some new and very weird physics that hasn't been seen before. For example, our results show that adding even a single particle to a lump of matter, however large, could in principle dramatically change its properties. New physics like this is often later exploited in technology, and already is by nature. The researchers are now seeing whether their findings extend beyond the artificial mathematical models produced by their calculations to more realistic quantum materials that could be realized in the laboratory, and more importantly, in our lives."
Now, the information contained in these first two papers is beyond anything that you can find within the hyperresidual itself. But please be rest assured that the hyperresidual does represent very real, embodied, embedded experience in this real world. To exist is to power set. And you can trust this little hyperresidual, it exists too. Il y a beaucoup de bon temps dans la sud de Louisiane. Hey! Analavos of the great hyperresidual. Let's describe what can't be described.
Let's start with power sets.
So again, it's a contradiction. So when I was teaching at Oxford, one of my students came up with the following different anthropomorphization of Cantor's argument. Let's consider all possible fruit salads. We have a given collection of fruits, apples and oranges and grapes, whatever. And a fruit salad consists of some collection of those fruits. So there's the banana, pear, grape salad, and so on. There's a lot of different kinds of salad. Every set of fruits makes a salad, a fruit salad. Okay. And we want to prove that for any collection of fruits, even if there are infinitely many different kinds of fruit, for any collection of fruits, there are more possible fruit salads than there are fruits. So if not, then you can put a one-to-one correspondence between the fruits and the fruit salads. So you could name every fruit salad after a fruit. That fruit might not be in that salad. Doesn't matter. It's a naming, a one-to-one correspondence. And then, of course, we form the diagonal salad, which consists of all the fruits that are not in the salad that's named after them. Mm-hmm. And that's a perfectly good salad. It might be the kind of diet salad if it was the empty salad, or it might be the universal salad, which had all fruits in it, if all the fruits are in it, or it might have just some and not all. So that diagonal salad would have to be named after some fruit. So let's suppose it's named after durian, meaning that it was associated with durian in the one-to-one correspondence. And then we ask, well, is durian in the salad that it's named after? And if it is, then it shouldn't be. And if it isn't, then it should be. And so it's, again, the same contradiction. So all of those arguments are just the same as Cantor's proof that the power set of any set is bigger than the set. And
a whole. Aleph null is the smallest countable infinity, and it's equal to the size of the set of natural numbers. The size of the set of real numbers is 2 to the power of Aleph null. Beth null equals Aleph null, which is the size of the set of natural numbers. Beth 1 equals 2 to the power Beth null, which is the size of the set of real numbers, and Beth 2 equals 2 to the power Beth 1, which is the size of the power set of the real numbers. So in general, Beth n plus 1 equals 2 to the Beth n.
And now for causal entropic forces.
So what you've just seen is that a variety of signature human intelligent cognitive behaviors, such as tool use and walking upright and social cooperation, all follow from a single equation which drives a system to maximize its future freedom of action. Now, there's a profound irony here. Going back to the beginning of the usage of the term robot, the play R-U-R, there was always a concept that if we developed machine intelligence, there would be a cybernetic revolt. The machines would rise up against us. One major consequence of this work is that maybe all of these decades we've had the whole concept of cybernetic revolt in reverse. It's not that machines first become intelligent and then megalomaniacal and try to take over the world. It's quite the opposite, that the urge to take control of all possible futures is a more fundamental principle than that of intelligence, that general intelligence may in fact emerge directly from this sort of control grabbing rather than vice versa. Another important consequence is goal seeking.
And now for the universal set, the null set. Engage symmetry.
Universal set. A set large enough to contain all sets under consideration in the current context. Universal set synonyms: universal class, universe. UNIVERSALSET. Universal set.
Hi, for this video what I want to do is talk to you about empty and universal sets. An empty set is also known as a null set sometimes, is a set containing no elements. That means that there is nothing in it. It could be a situation as described and there's nothing that matches it. But anytime you end up with something that is empty, it's denoted by either a circle with a line through it, or you can use the set brackets with nothing inside. So these are the two ways that are used to denote empty sets in mathematics. So an example could be rolling a 7 on a die. This would result in an empty set because when you're rolling a die, you can only end up with the numbers 1, 2, 3, 4, 5, or 6. And so like if you were looking for the probability of rolling a 7, that would be 0 because there aren't any. Your result is a empty set because there is nothing that matches that. Okay. The other one that I want to talk to you about is a universal set. A universal set will change from problem to problem. It's the set that contains all of the elements for a specific situation or a given problem, and we denote it by the capital letter U. So a couple examples that you might encounter would be all the letters in the alphabet. So if you ended up with a letter that was in the alphabet, then it would be contained in your set. If you ended up with something like, say, a number, then it would not be contained in that set. Okay. Another example would be the numbers 1, 2, 3, 4, 5, 6. This would be the set of all values that can be rolled on a number, or on a die, or a number cube, as they sometimes call it in some textbooks now. But it's just the numbers 1, 2, 3, 4, 5, 6. Another example could be the set of all real numbers. So it really does change from problem to problem. So a universal set is dependent on the information that is given to you. So a lot of times it will be given to you in the directions. It will say for this set use this universal set, or for this set it has to be a real number. So if it's not contained in there, then it would result in an empty set.
And then there's one very special example of a set I'm going to illustrate. It's the set with nothing in it. Squiggly brackets with nothing. This is an empty box. And we give a special symbol to associate to that set with sort of 0 with a backslash to it. This is the empty set. Now, I should note that mathematicians do actually go a bit further than just agreeing as this is a foundational concept. There's a list of axioms that specify the different properties that sets have to have. The Zermelo-Fraenkel axioms are the most standard way that mathematicians have agreed on the basic concept. But either way, we're saying this is the base, and we're all just going to agree on what that means. Okay, so let's do something with that. I want to now interpret what is a number, because a number is not a set. I've talked about the set that contains numbers, but what really is a number? Could I interpret numbers as just being a special type of set? So basically what I'm going to do is I'm going to look at the natural numbers, 0, 1, 2, 3, and so forth, and try to associate a particular set to each of them. So the first one I'm going to do is I'm going to associate 0 with the empty set. I'm drawing an arrow here relatively loosely, and what I'm trying to say is that the concept that you and I have in our minds of 0, I'm going to interpret that in terms of the language of set theory by associating to it the empty set. Indeed, the empty set is not nothing, it is a set with nothing inside of it. And so this association makes sort of sense because I'm associating 0 with the set that has 0 element inside of it. Likewise, let me take the number 1, and 1 is associated to a set as well. It's associated to the set with 1 element in it. The element is just the empty set. So I think of this as a box, that's the big outside set, that contains the empty set. This is a box within a box. Okay, let me keep going. What about 2? 2 I'll define to be a special type of set that has 2 different elements into it. So let's make this different association. 2 is the set that contains, well, both of the previous ones. It contains the empty set, and it contains the set that contains the empty set. So in other words, at the level of the outside box, this biggest box, there's 2 things inside of it. There's an empty set, an empty box. And then there's a box that contains an empty box. There is the set that contains the empty set. Okay, so...
If we have something that has a value at every location in space and time, this is called a field. So this information that you add, that's what's called the gauge field. Gauge phases field moving electrons. What? Bear with me. I have an example. Suppose you have an old version beam balance. If you have the same length of beams on both sides and the same weights, it's in balance. Now let's say that adding weights is like shifting the phases by an arbitrary amount. If you add the same weights on both sides, nothing changes. This is like saying the physics remains invariant under this arbitrary choice if it's the same in both places. But if you add a bigger weight on one side than on the other, that ruins the balance. This is like setting a different phase in one place than the other. This is your gauge. But that'd mean the physics depends on this arbitrary choice. Not good. So what you do is that whenever you add a weight, you also adjust the support of the balance arm. This is what the gauge field does. If you change both together, you always keep the balance. With the gauge field, the gauge doesn't matter. This is basically how gauge symmetries work. You tie 2 changes together so that the net cancels out. And you do this because quantities which are physically measurable shouldn't depend on arbitrary conventions. With about light, so the thing is that once you introduce this gauge field, it develops a will on its own. It's there to keep the electron phases properly lined up. But it can do things even if there's no electron inside anywhere. In particular, it's got ripples that can travel, and those are the photons, the quanta of the electromagnetic field. They are what light is made of. Again, this is very similar to Einstein's theory. Space curves around masses. But even if there are no masses, space can have ripples that travel. In Einstein's theories, these are the gravitational waves for the electron. They are electromagnetic waves. So this is why we have light, because we have electric charges. Another thing that you can learn from this is that you can't have an electron without an electric field. You knew this already, but I think it's a somewhat underappreciated point because it means that this electron in the STEMNAT model chart, it doesn't exist. We've never seen it. The electrons that we actually observe, they always have a cloud of photons around them. This idea is called gauge symmetry. So we have light because we have electric charges. You might then ask, well, why do we have electric charges? Physicists don't have a good explanation for this one. They've certainly tried. They've tried with unified theories and theories of everything, but none of those have really worked so far. Personally, I think the reason we have electrons is because it's the simplest particle you can think of. It comes from the simple symmetry there is in all of mathematics, just this one phase. Indeed, getting the electrons and the light with them is the easy part. The difficult part is explaining all the other properties of the sunlight model. But regardless of how you look at it, gauge symmetries are how nature works. And that's why light exists.
Our external physical reality is a mathematical structure. That is, the physical universe is not merely described by mathematics, but is mathematics, specifically a mathematical structure. Mathematical existence equals physical existence, and all structures that exist mathematically exist physically as well. Observers, including humans, are self-aware substructures. In any mathematical structure complex enough to contain such substructures, they will subjectively perceive themselves as existing in a physically real world.
Thank you for walking down this mathematical journey with us. Hey! Peace.
God is beyond description, but me, I'm gonna go ahead and try. This is the Analavos of the Great Hypersigil. Now, I just learned what those words mean, but rest assured the experiences and symbols contained therein are very, indeed, could be found if you ran past the site. Where was that, though? This is Analavos of the Great Hypersigil. Now, I just learned what those words mean, but rest assured that the symbols and experiences contained therein are indeed very real. At the top, we got Dieu au-dessous de tous, God above all. And that's just the understanding that to exist is to be embedded in a greater system. The angels over our left and right shoulder represent the pros and cons, the proximity to and distance from God. After that, we got the power set, or power setting. The power set is ta mata mata. It is the knowing of what you already know, the taking of what you already have to produce a universal gain. It is Jocho. It is the focusing of a problem in a mindful manner and letting and interacting with the internal universal mathematics inside of you to put forth a universal gain. To power set is to exist. Après ça, tout le monde chez Dieu. Everyone and everything is in the house of God. Now, whether that thing is your dreams and accomplishments or your nightmares and machinations, all the stuff that shines in the sky and darkens the void, is within such a subset. Then there's the universal set, the place where everything's already worked out. And then from that, we take a little bit of nothing and a little bit of mystery or variability. And that element of nothing provides us with a lot of calculable gains. And that mystery element of X kind of gives us some range and some mystery. And those two together kind of work as our gauge symmetry in relation to the universal set itself. Then we got the force of intelligence. Any set embedded in a greater universe is going to actively resist the control and constraints it finds itself under in a way that increases its future freedom of action and actively overcomes the control and constraints that gave rise to it. And that's just causal entropic forces. That's just movement forward in the physical universe, period. And then we'll finish with basically what we started with. To exist is to be embedded in a greater whole. Outside that, there is nothing. Inside that, you got a lot with you. And for that, we thank goodness. For that, we thank God. For that, we thank power sets and power setting. We appreciate the all worked outness of the universal capacity of things. We appreciate the physical nature to overcome and get better and increase freedom of action. Tout le monde chez Dieu. Dieu au-dessous de tous. C'est tout. Paix soit avec toi. Ainsi soit-il.